Good evening, everyone. I'm David Burney from the Burney Group. I'm glad you could all join us tonight. We're really excited to have a exciting discussion around artificial intelligence and the application of AI in operations. I thought I might introduce myself, the team, and hand it over to Doug, who will introduce our speakers for tonight. Very quickly, I'm David Burney. I'm the principal and founder of the Burney Group. The Burney Group, I founded in 2011 after having worked at McKinsey for about 8 years, and I thought there was just a great opportunity to bring together management consulting insights with the best-in-class technology solutions to really help transform the operations of our clients. And so we've been doing that since 2011, focused on areas such as robotic process automation, blockchain, and of course, artificial intelligence. So we're really excited to have you all here tonight. We're of course thrilled to have Mike, Frank, and Catherine, who are here tonight to speak and to be our panelists. Doug will give a formal introduction to them. So I just wanted to do a quick introduction of Doug before turning it over. So Doug is the head of our innovation practice. Doug worked at IBM for over 20 years, and he decided to come back to Canada, and it was a great opportunity. I ran into him and I said, hey Doug, why don't you come and let's work together, and let's focus on innovation. And it's just so exciting and so much fun right now to be in Toronto and be part of this amazing transformation that's undergoing. From automation to AI, blockchain, we're really at the center of it in Toronto, and it's great to have Doug and others on the team. So without further ado, I'll turn it over to Doug to introduce our panelists and our guest speaker. Thank you.
Good evening, everyone, and a hearty welcome to everyone. Thank you very much for joining us. I have the privilege of introducing our keynote speaker, who is a friend and colleague and mentor. Mike Rhodin spent 33 years at IBM, rising to become one of the company's key leaders. He was the senior vice president and an officer of the company. He was responsible for the creation of IBM's software solution business, including much of its Smarter Planet portfolio. After a demonstration of the Watson system on Jeopardy, Mike founded IBM's Watson Business unit and used this groundbreaking technology to launch a cloud-based service and first industry vertical, Watson Health. Prior to that, Mike led many large-scale organizations inside of IBM, including its European operations based out of Zurich, as well as its collaboration business unit. He is an established technologist. He's run numerous engineering organizations within IBM in office systems, networking systems, as well as the very early stages of IBM's Internet of Things technologies. Since his retirement from IBM in 2017, Mike has taken on a number of independent director roles for many organizations, ranging from advising startup companies in the incubation phase, advising venture capital firms, and serving as a board member on private equity-backed technology companies such as HZO, or HZO here, SyncSort. In addition, Mike has served as the supervisory board on the board of TomTom, based in Amsterdam, and the International Advisory Board for Group Santander, which is a leading international bank based in Madrid. Mike is also on the board of directors of Mars Innovation here in Toronto, and he's actually in town for a board meeting tomorrow, and so we're all very thankful for his contribution to our local ecosystem as well. He actually grew up in Toronto. He actually went to Martin Grove Collegiate. I'm not sure if anyone else here is from Martin Grove, but Mike spent many of his formative years here in Toronto, so in some ways it's a little bit of a homecoming for him. And without further ado, Mr. Mike Rhodin.
It's all right. Good afternoon, good evening. Sorry to take everybody away from the wine. Hopefully people brought glasses with them. That's the important part. To kind of build on Doug's story, I am American. I was born in the U.S., but my parents transferred us to Toronto when I was in the 4th grade. We moved to the west end of Toronto. My dad worked here we were here for 7 years. So most of finishing elementary school, all of middle school, and most of high school were here. And then like all good parents, they ripped me out of my high school the summer before my senior year and transferred us to Calgary. So I finished my education in Calgary before I headed back to the U.S. for university. My brother actually went on to go to the University of Calgary, was an all-Canadian basketball player, and we've had all sorts of, and my sister-in-law is Canadian, so we've had all sorts of interesting mix. My youngest brother was in Canada from 6 months old till he left in his late teens to go back. So we have a lot of ties back to the area. And one of the exciting things about joining the Mars Innovation Board a little over a year ago, and Rafi, who's somewhere in the back of the room, was that it gave me an opportunity to come back to Toronto on a regular basis, where I've actually reconnected with all of the guys I went to high school with. And kind of the craziest thing, they all still hang out together, right? 35 years later. And we all actually got on a plane and went to Scotland together this summer. So it was pretty interesting to be back here. So, when I left my Canadian education, went back to the U.S., I went to the University of Michigan and became part of the computer science department there. That was back in the 70s. Computer science was a small department that was headquartered in the basement of the oldest building on campus. Right? It was not part of the engineering school at that point in time. It was considered separate from engineering. Engineering dealt with real computers, the hardware stuff. And the software stuff was kind of the touchy-feely stuff that was over in the School of Literature, Science, and Arts. Today, I'm the chair of the advisory board for the Computer Science Department at Michigan, which is now part of the engineering school, the largest department on campus and in the prettiest, most well-equipped building on campus. So it's amazing how over the course of a career, things can change so dramatically. So, coming out of Michigan, I went to work for IBM. Doug kind of went through the litany of my background. I won't repeat that. But I spent a long time in IBM, working my way up through the company, through different roles. But like many people, I watched a particular demonstration of a new technology on a game show called Jeopardy. And I went into the office the next day and said, I have to have that technology. Right? That was, it was very clear in my mind. I had to have it. I went to the office. I started politically working on acquiring it because I wasn't the only one with that idea. But I managed to prevail and get a hold of the technology and start building it out. So what Doug's asked me to do is kind of set the stage for the panel discussion tonight by going through some of the history and definitions and some of the stories around things that were going on around AI, are going on around AI, and kind of where things are going with AI, as well as some of the things to worry about as we move into this field, right? So, AI itself is pretty straightforward. It's the idea of the intelligence of machines. It's been talked about for a long time. It's been written about by great literary people like Bradbury, Asimov, all the science fiction writers of the early 30s, 40s, and 50s, theorized about many of the things that we're actually turning in and making a reality today, right? And AI really is the science behind making those stories real. Many great things have been first introduced to us in the realm of science fiction. It really captures the imagination of scientists or future scientists, and they go off and try to make them real. Right? I mean, many of the things that we're living with today are things that were demonstrated on Star Trek in the 60s. Right? So we see this idea of things moving forward. The road to how we got here is pretty dramatic. There's been a lot of fits and starts over a very long period of time. If you go back to the late 40s, when we were first building the first electronic computers, people started theorizing this idea of smart machines and talking about it and started thinking about how you could actually do it. I'm going to use a particular story to kind of work through this timeline that ties back to the problem that we were working on with Jeopardy, when a gentleman by the name of von Neumann, who was the originator of the binary architecture that's the foundation of all of our computers today, the 0 and 1 system, said that someday computers will be able to answer any question. Right? In the late 40s, right? People were like, how? Right? But like all good theories, people started working on it. They started looking at algorithms. They started working on use cases for some of those algorithms. Things like voice recognition systems were worked on. Throughout the course of the 50s, the 60s, theoretical algorithms were described, they were discussed. People started to work on the problem, trying to figure out how it would work, but very much theoretical during that period of time. Going into the 70s, similar story. By the time I reached the point in my computer science program at Michigan, I took all the classes on AI I could find. I was fascinated by the topic, but we couldn't really build them. Right? We could study them. We could write little sample proof applications to test out little pieces of the theory, but there were some fundamental limitations that we couldn't get past as we went forward. So the ideas still remained kind of out of reach. Right? They were discussed, but it was still an esoteric field of study. In the 1990s, we started to see some business people and technologists try to take a run at AI in the consumer space. Some of you in the room may remember the subject of knowledge management systems based on expert systems. There was a lot of hype in the late 90s, 96, 97, 98 kind of time frame. But the systems kind of fell flat. They didn't really take off. And there were some fundamental flaws with the idea. I think that the simplest way I think about it is the core idea of the knowledge management systems is you could get a human to sit down and type all of their knowledge into a system in the form of rules. Right? We couldn't find any of those humans. Right? That was the problem. And so the systems kind of went away. Rules-based systems, kind of went on to business process reengineering. We started adding a lot of capabilities into transactional systems around rules-based systems, fairly narrow in scope, very limited domain, but they became very useful techniques. But the idea of general knowledge systems really was still out of reach, right? So why was it that we weren't able to get there? What were the things that we thought were problems? Well, one of the reasons when I was studying it is that we couldn't actually build the systems because we didn't have computers that were powerful enough to actually run the algorithms. Right? The algorithms required an awful lot of computational power to run in parallel at scale in order to achieve what had been theorized in those applications. The second problem that we had was that even if we could build a computer that could operate at scale, do all of those calculations, we didn't have enough digitized data to power and train the systems. So we had two fundamental issues that were kind of holding us back from making the progress that we wanted to make in the field of AI. So one of the things that companies started to do is they started to use demonstrations to prove that milestones were being achieved on progress. The computational power milestone that I'll point back to because it ties back to my career was in the late 1990s. How many people remember a system IBM built called Deep Blue? Right. The demonstration was of a game called chess, right, playing against the world's greatest grandmaster. Right. So the idea was, could we build a system that could beat Garry Kasparov at chess? Right. And we did. But most people don't remember that we played twice, 2 years in a row, and we lost the first year. Right? We knew we would win the second year because at that point we knew that the curve on the computational power was going to put us to a point that we'd be able to overcome the limitations of the prior year system, and we knew that it would just keep getting better from that point forward. But one of the things that I think is important about that little lesson is that we played twice is that we're starting to see systems emerge and being demonstrated that are really non-deterministic. They're not always going to win. They're going to make mistakes. They're fallible, like humans. Right? So that becomes one of the characteristics we have to watch for. So in the late 1990s, we reached a point where computational power was no longer the inhibitor. Right? We could start building systems And the chess system itself was a machine learning system. It had those algorithms in it, but it was still a fairly narrow domain set, right? So what was happening in parallel in the 1990s that could start to attack the other system, the other limitation? Mid-1990s, little thing called the World Wide Web became possible. Initial business disruption for the World Wide Web, or the one that I think is the initial one, content publishing. People started putting lots of information about their companies online. They started to figure out how to publish things online. Second big application. People realized that once information was online, maybe people could buy things online. E-commerce systems started to emerge. More information was put online. People started to think through these systems as communications vehicle, initially point-to-point or one-to-many. Email systems became interconnected on the web. We started to see an explosion of connectivity across people. Then people started to realize that if I could talk to one person or a small group of people, maybe I could talk to everybody, right? With the advent of social networks, right? Each of these breakthroughs is putting more and more and more digital content online. The ideas start to cross over. We start to see ideas merge. So the idea of content publishing and social networking together gave us the concept of the wisdom of crowds, and we saw things like Wikipedia emerge, right? Where a collaborative group of people are getting together to create a knowledge base online that everybody is socially keeping up to date and trying to keep it current, which it does a pretty good job of. And in fact, the core knowledge base in the Jeopardy system was Wikipedia. Right? So we're starting to get to that point where enough data is getting into the systems as we go forward. So the 2000s was really about the data coming forward. Now, that little hypothesis that von Neumann made about computers being able to answer any question became known as one of the great computer science challenges over the course of 5 decades. It was called the open domain deep Q&A problem. Could you build a system where you could ask a question about any subject and get a good human-like answer to that problem? A group of researchers in 2007 in IBM started to work on that problem. There was 27 PhDs. It's been described by a colleague of mine from Carnegie Mellon as kind of a Manhattan Project-like group, where it was cross-discipline. Lots of different capabilities, and we kind of locked them up as a team. I'd like to joke that we kept them in a fairly small room. The room was about this big, about half the size of this room. The 27 researchers were in that group together. My usual joke on that is we just threw pizza under the door on a regular basis to keep them going. But they did work on this for a while. They started to make some great breakthroughs, particularly around natural language processing, which we'll talk about in a minute. And those breakthroughs led them to a worry, which was, what if no one believes we solved the problem? Because there was no agreed-to proof for a solution to the problem. So they held a colloquium. Out of the colloquium, there was agreement that if someone could build a system that could play the game show Jeopardy, that would be viewed as an agreed-to proof of the open domain deep Q&A problem. So hence, that's where we started building the machine towards Jeopardy and training it on Jeopardy. Sony had some preconditions for us on that, because Sony owned the game show rights to Jeopardy. Their biggest one that probably gave us the most fits was that the system had to press the button just like the humans did, right? So behind that pretty avatar that was on the screen was a really ugly mechanical thumb that pressed the button so that it was just like the humans in the game. So the system went on, and we went through the process, and then on Valentine's Day of 2011, we actually demonstrated the system online, and when we did, we didn't know who the victor would be. Right? It was not a certain outcome. So it wasn't that we had built it knowing we were going to win. We knew we would be very competitive and could win. But there's still, it is a game of chance. There are things in that game that could make it go either way. But some other things popped up during the playing of that game that I think captured people's imaginations. And one of them was Final Jeopardy on day one when it got the answer wrong. I think the answer was Toronto, if I remember right. But Toronto, right. But that's right, you're right. But the idea that a machine could get a wrong answer after being so right throughout the game kind of made people start to think that, wait a minute, this is something completely different than we've seen before, right? So we had an interesting experience. We got through, we won the game, but the following days we started getting a lot of very interesting phone calls from people that had been watching the game, and that became kind of how we kick-started into the business and got it launched. And we'll go a little more into what some of those solutions were in a few minutes. So let's go back and look at what's underneath these systems and this idea of the data and the digitized data. I believe, and this is something I started working on before I retired from IBM, was that we were really starting to see the beginnings of an information supply chain emerge. Right? We were seeing sensors being placed all over the physical world. Those sensors were generating huge amounts of data, 99% of which is completely useless, but huge amounts of data. But what's interesting is it's not the useless data we're interested in. We're interested in that 1% that's very interesting. We need to find the signal in the noise, right? We need to find that signal. We need to use analytics to find it. Then we need to try to turn that piece of data into information. We need to aggregate that information with lots of disparate sources of information and feed it into AI systems to create knowledge. The end result of this is that we will be able to start to build systems that will enable us to scale human knowledge for the first time. Right? Why do I say scale it for the first time? It's a volume problem. It's the amount of data that we're dealing with has surpassed the ability of humans to consume that amount of information. Now, if you just look at simple domains like healthcare, the amount of information that's being created in healthcare is mind-boggling. But then you throw on genomics and the information about the biome on top of that. It's such a volume of data that humans can't consume it all and correlate it in a way without the help of machines. That's what's really exciting about what's going on now. We've crossed the barrier of the computational power. We've crossed the amount of digital data. And we're starting to figure out how to put together the information and that supply chain of information so that we can feed these systems at scale, and we could build systems that can help humans scale human knowledge. That's what I think is truly excited about where we're going right now. So there are three basic types of AI, right? First, there's narrow intelligence. This is where machine learning algorithms have been used in a fairly narrow way in applications. You can think of things like Siri, right? You can think of things like the chess game we talked about, fairly narrow space. It was a complicated win in the 1990s, much easier system to build today than it was then. But it was a fairly narrow space. Then we start to see more interesting applications start to be built, right? Things that are starting to deal with cancer treatment systems, drug discovery systems, legal advisors, dealing with much more complicated, wide-ranging topics and systems that can work with us as opposed to just for us, right? And then finally, there's this idea of artificial superintelligence. Some people in the industry call it the singularity, the point when the machine intelligence surpasses human intelligence and the machines take over, right? This is still the realm of science fiction. Right? It's still in the realm of what was described in all those great sci-fi books. I haven't seen the breakthroughs that get us there yet. But there are people predicting, just like we were able to predict when we'd be able to beat Kasparov and when the computational power and the amount of digital data were going to be created. People like Kurzweil and Peter Diamandis are talking about the mid-30s, to the late 30s as a time period to get there. I think it's probably, that's a little ambitious, but we're starting to see an awful lot of people working in the field. We're starting to see an awful lot of breakthroughs, and some of those breakthroughs are accelerants, right, to how these systems are going to be built. Right? Beneath these systems, you hear the word machine learning. Machine learning is a type of algorithm, right? right? Many of the algorithms that were theorized during all that work that went on, the basic machine learning algorithms are underneath all of the voice recognition systems that we're working with today. But in many ways, the basics are systems that go through a supervised learning track, just like we do, just like humans do, where we're taught how to do things. And then once we're educated, we can start to operate in an unsupervised mode where we're working on real-world data and starting to operate in the wild, if you will, right? We're starting to see new approaches leveraging machine learning algorithms to dealing with large amounts of data and organizing and looking for the patterns in it around neural networking and deep learning systems, which we'll talk about next. Deep learning systems, I think, continuing with the theme of AI breakthroughs being demonstrated by games, I think Google made one incredible breakthrough over the last few years, and that was the AlphaGo system, a system that played the game Go. How many people watched that and followed it? What was unique about that system is they were working on, in many ways, one of the key problems, I think, with systems like Jeopardy, the Jeopardy system or the Watson system, which is the training process, right? Moving into an area where you've got the ability to do observational learning, right? Their system learned how to play Go by watching people play Go, right? Figuring out what the rules were and getting better at it over time, right? So that's another learning technique that we as humans use, right? That we now have a demonstration vehicle of, again, via a game, but becomes a new tool in the kit bag of people trying to build complex AI systems, right? What we're going to find is complex AI systems are not one algorithm, one type of learning, one type of data. They're going to be all of them kind of blended together in order to solve particular problems, right? And we'll talk about some of those more complex applications. Cognitive computing, which is a phrase that IBM was using when I was there, when we brought out the Watson business, is really starting to get at this idea of the beginning of those complex systems that are starting to do decision support. It really is starting to help us think with the data, if you will, learn how to use the data, and actually become a collaborator with the applications in those systems. All right, so more, starting off with more complex deep Q&A, but really leveraging that ability to build interesting applications out of it, right? One of the ones that we worked on very heavily was in the cancer treatment space, right? Could we actually build a system that you could train it on chemistry, biology, anatomy, all of the things that doctors go through in their training, specialize it in cancer, lay in all the drug information, all of the information about drug adherence, drug conflicts, side effects, all of that stuff, train it on all of that stuff, and then build a system that could actually take patient information as an input and try to figure out if we can come up with potential treatment options for that patient based on the best medical information in the system, but also based on family history, medical tests, and everything in the medical record, kind of bringing those two together, right? That's a more complex system. That's not just a Q&A system that's trained. It's actually more of a decision support system that's built leveraging AI technologies, right? So cognitive computing is that. On a simpler level, you're starting to see lots of companies building these chatbots. One of the ones that kind of took us by surprise was a professor down at Georgia Tech decided to build a teaching assistant for his class and test it with his class without telling his class. So he introduced a chatbot as a teaching assistant, didn't tell the class. The students interacted with it all semester long, voted it as one of the best TAs in the class. And they didn't catch on. And the system was, the TA's name was Jill Watson, right? So it was an interesting use of trying to test out on his own class whether these systems were getting to the point where people couldn't tell they're actually getting the information from there. But what that points out is a very interesting use case for these technologies. If you think about the problems with MOOCs and some of the online education systems, they're very rote in their interface and they're very dry, and people don't, they start them and they get lost and then they don't go back. What if we could make that interface much more dynamic, right? Much more like the teaching assistant, the professor kind of dynamic back and forth on top of that knowledge that's already been digitized. We could start to create something truly disruptive in the field of online education, right? So just a couple of examples, right? The other field of study that's getting a lot of press right now is machine vision. A lot of great work that came out here out of the University of Toronto with the 2012 project that was on the timeline. This is going beyond the ability of systems to deal with human language, but actually now to see and recognize things in our world, right? Field of study in this, or the use of this is being done in things like autonomous vehicles, which is what we're doing at TomTom, is we're building real-time navigation systems, real-time mapping systems, high-definition maps to feed into autonomous driving vehicles. Because it turns out that you need really good maps when there's no human interpreting it at the steering wheel, right? So when you move from human drivers to machine drivers, you need better information. And you need information that can actually follow that information supply chain that I talked about, so that the car in front that sees the new pothole can feed that information from the sensors through the system to the cloud, transactional updates to the map, so the cars down the road behind them are going to have an updated system that knows there's a big pothole in the road ahead. That kind of closed loop system is becoming the art of the possible as we move forward. Right. We're also starting to see lots of breakthroughs in the field of medicine around computer vision, studying medical images, starting to figure out what radiologists need. One of the interesting things about technology is we tend to generate more and more stuff, right? Medical imaging is no different. The new imaging techniques are generating orders of magnitude more images to be looked at. The problem we've got is we're not generating orders of magnitude more radiologists, right? So we've got a situation where the volume problem is now overwhelming the profession, right? Which is a consistent theme that we're starting to see as we go forward, right? Natural language processing, which was really much of the core breakthroughs in the Watson system. Remember I talked about the problem with the knowledge management systems and getting the human to sit down and type their knowledge in? What we did with the Watson system was make it so we could just read human language. We could actually take the input directly off the web. We could read Wikipedia. We could read important documents that are important for Jeopardy. So there was the religious category, so we had to read all the religious documents. We had to read IMDb, because everyone knows there's always a category on who was in what movie and when. So there was all sorts of interesting things we had to learn how to read. But because of the variety of kinds of information that had to be read, it actually forced the system to have to become much more general purpose at its input level, right? So that became important, right? So we solved that upfront problem. The system was focused on how we can deal with human language, whether we can answer questions and come back with answers. But even the Jeopardy system was limited, right? In that it became really, really good at finding one-word answers to complex questions. But it turns out when you go from one-word answers to paragraph answers and page-long answers, it becomes a much more significant problem, right? So we've now got systems that are focused on language, vision, decision-making, right? So speak and hear, see and think, right? That's kind of the way to think about where the breakthroughs are becoming and the milestones. A lot of these are in different projects. All of the pieces aren't in one place yet, but they're starting to be pulled together. One of the things that I think some very smart companies are doing is they're starting to focus kind of on an orthogonal path, and they're trying to capture a new interaction mode for dealing with information systems, right? We're all guilty. We're all using these things. How many people have used Siri, right? How many people have Alexa or Google Now, right? These systems are capturing us as users. The back ends of those systems in many cases are more rules-based, skills in Alexa's case. But once they capture the user experience, they can change the back ends out at will for more sophisticated AI systems over time. Right? So they're capturing the interaction model. That's shifting from just voice to video. We're starting to see more systems pop up. Facebook just launched their portal system. So not only do we have Alexa listening to everything we do in our house all day long, we're now going to have portal systems looking at us all day long, trying to see what we're doing. So we're going to see more and more of these systems become both audio and video, right? They're going to be capturing huge amounts of information. Make sure you read the fine print in the T's and C's of those products you buy before you check the box as to what they're doing with that data. But these new interaction modes are fundamentally changing the way we're going to use information over time. Information technology systems have been using a common interaction mode since 1982. Right? That's when the commercialization of graphical user interfaces hit after Apple and Microsoft stole it from Park Research. Right? They launched it. The graphical user interface became the way we've all used it. We've made them smaller. We've put them in more places. They're on ATMs. They're on phones. They're on tablets. They're on TVs. They're all over the place. But that interaction mode becomes how we dealt with information systems for decades. It's starting to change. And the capture of that information by these companies has become, I think, a brilliant business strategy on the part of Amazon and Google, Facebook, and many others, because they're trying to capture people, right? And these information systems that are going to get built behind it are going to be how they start to monetize that over time, right? Oh, missed one, right? So we talked about audio, voice systems. We talked about visual systems. What else is starting to emerge is we're starting to see systems that move into our world in a three-dimensional space. Robotic systems, tactile systems, things that can touch, things that can move around. So just a simple use case to kind of put in your mind to think about why this is interesting as opposed to a toy. We worked with a company in Japan that had a robot. It was SoftBank. They had a robot called Pepper. The use case they were envisioning is Pepper with an AI system and an AI back end as an elder care robot at home with their grandparents. Why is that important in Japan? They have a rapidly aging population. They have really low immigration and a low birth rate. So they have nobody to care for the elderly. They had no place for them to go. So systems that could actually move around in our world, that could see when someone's fallen down, when they're not breathing, when they're having a heart attack, help them order food, bring in goods to the home. Those kind of systems become useful. So you can see the allure of these kind of systems moving into our world, and the back-end systems are starting to get interesting enough that you could put that system together, right? Maybe in a rudimentary way at first, but it would get substantially better over time, all right? Building AI applications is very different than building traditional applications. The first and foremost problem in building an AI system is what information base are you going to build? How do you curate that knowledge, and how do you keep it current over time? That becomes really important, all right? If you're building a radiology system, you do not want people making up stuff that gets put in your database, right? Anything that's going to deal with the human condition from a diagnostics viewpoint, you want to control the curation of the information and the training that goes into those systems. So thinking through the information becomes one of the biggest challenges in building any of these systems, right? The second thing is you have to get used to the ideas. It's not about the application, it's about the knowledge base. And the knowledge base gets trained as well as the application, right? So part of that supervised learning phase and then the unsupervised learning phases is starting to build the application and train it how to use the information base. The information base is the asset, the most valuable asset. The systems become interesting, they learn over time, but then the programs that use those systems become fairly straightforward, right? The chat bots are basically calling Q&A APIs, fairly straightforward. What the Q&A API is attached to is what's really interesting. So it's a different problem space. So what's happening is we're moving from a world where the program was the most important thing to where the information is the most important thing, right? It's a different era, right? It's an information era as opposed to a programming era. Right. So the question that we're all facing, and hopefully the question for our panel tonight, is these systems are getting ready for prime time. We're using them. Many of us are using them without knowing it, which is okay. That's actually a good way to introduce it. But these systems are going to continue to evolve, and we have to get ready for it, both in business and in our personal lives, because it's going to be hard to tell the two apart over time. Right? It goes back to the volume problem I was talking about. I think the simplest way to look at it, and what I used to tell my teams was, as they started to think of use cases for AI technology, start with looking for professions where the volume of information being produced has overwhelmed the ability of the professionals to consume it. Right? Very simple test, right? Because if you can find that space, you found a use case for AI technology, right? It may not be an easy use case, but you found a use case, right? And professions that have historically been hard to deal with automation because of the knowledge-centric nature of what those professionals do, are going to be automatable with these new systems. Doctors, lawyers, radiologists, regulators in the financial services space. We're going to be able to see things change pretty dramatically as these capabilities come online, right? These processes in these industries for these professionals are very people-intensive processes. There's a lot of decision-making going on. There's a lot of interrupts that are going on. Over time, you can start to take nodes in here and start to use a robotic process automation to start to automate pieces of this, but there's still decision-making bottlenecks that occur as you build it. And now we can start to add in AI-based decision-making in the middle of the robotic process automation, bring those two together, and we start to eliminate or take the friction out of a lot of those bottlenecks, making things more efficient, making processes work better. You're going to start to see this kind of technology layered in with things like blockchain, which are aimed at taking the friction out of multi-organization process flows. That is going to be quite powerful as these systems come together. Right? Some industry examples. In the healthcare space, the thing that brought the doctors at Memorial Sloan Kettering to IBM after the Jeopardy match was actually a very simple thing that was based on a complete afterthought in the Jeopardy system. We were worried when we built the Jeopardy system that people wouldn't understand what they were watching. So we put a little green box on the bottom of the screen that showed the top 3 answers, and we showed the confidence level associated with each of those answers. When the physicians called, they had a couple questions for us. The first one was, how many answers are there? And we said there were thousands. And they said, okay, good, that's what we hoped the answer was. The second was, how do you figure out the confidence level? And we said, based on the supporting evidence behind each of the answers. And they said, perfect, that's exactly what we're looking for. Because it turns out, what a doctor does every day is gather large amounts of evidence to form a list of hypotheses and come up with the particular hypothesis they have the most confidence in for that particular patient. Right? The problem they were facing is that the amount of medical information is doubling every 24 months. And if you think about how long it takes to train a doctor, my niece is now 8 years into her training. Right? She's graduating from Duke Medical this spring. Where she will enter an internship and a residency, a surgical specialty, and 15 years into the process, she'll start practicing. Right? The half-life of that medical education is being attacked by the rate and pace of new medical breakthroughs. Right? So how do we actually bring those two together and leverage new systems that can start to help doctors deal with what's going on? Because we believe the rate and pace of medical breakthroughs is going to have again and then have again after that, right? So we're seeing that. In the financial services space, we talked about chatbots earlier. The first use case, the immediate $ use case looked at in financial services, how do we take call center costs out of our company, right? It's one of the biggest cost drivers and dissatisfaction drivers in many parts of financial services institutions because A lot of people don't like to work in call centers, so that the cost is driven by hiring and training. Then they quit, and you hire and train, and they quit, and you hire and train. It's just a cycle that you get into. So the theory is if you could build a system that could start to answer 60% of the low-hanging fruit, you might be able to take 40% of the cost out of the overall call center. If you could do that, that's a big win in that space. But that was kind of the logic. I don't know if anyone's got to that level of takeout yet, but that's kind of the track record people were heading towards. On the other end of the spectrum, just as I was leaving IBM, we started working on, and I think we might get into a little of this discussion a little bit later, one of the systems we started working on is, could you actually teach a system Dodd-Frank in the United States? Could it learn the regulatory compliance framework required of all banks operating in the United States? That document is about this thick, right? And it's based on a lot of other documents and a lot of other regulations. So the question was, and if you think about the process that a bank uses, every major bank in the United States has thousands of people who are consultants, ex-regulators, and lawyers that are determining the compliance control framework and adherence to that control framework for that institution to make sure that they're in compliance with Dodd-Frank. The problem is there's a couple thousand people that are operating on their interpretation of what all that documentation means, right? So every bank has a different set of a couple thousand people. So every group looking at this has a different interpretation. So it keeps lots of opportunities for the regulators to find lots of irregularities in the financial services space. One of the questions that we asked was, if you could train an AI system to be a common interpretation of the regulatory environment, then you could build automated control frameworks that tested itself against that regulatory information base or information system every day. That would be a huge win because it would be a common interpretation. What would make it a mega win is if you could get the regulators to agree that that interpretation was correct, right? Then you've got a system that you can start to automate between there. And then the grand vision, the one that is, I don't know if we'll get to, is what if you actually changed the process on the regulator side, so when they wrote a new regulation, it tested itself against the framework, so the regulation knew if it was conflicting, or the author knew if it was conflicting, also knew what banks were going to be affected, right, and what the effects would be. That's an end-to-end process from the making of law through the implementation of law in a very complex space that could be done at scale, right? I think it's possible. I also think it's going to be one hell of an application, right, to build, right? But I know there's people working on the space, right? So lots going on in the space. We talked about automotive. What these new technologies are enabling us is to move from the world of innovation, where we're incrementally improving the things we do, into the world of disruption. Simple definition for disruption: making new things that make the old things obsolete, right? Disruption is actually how a lot of these technologies are going to come in. We're going to see lots of companies doing new things. Someone comes up with that regulatory compliance thing and can scale it, right? It would be hugely disruptive to the financial services implementation and the legal profession and consultants, right? And the regulators, right? That might be good, right? But it is a disruption, right? It's going to be broadly impactful across just about every industry. I haven't seen an industry that isn't going to be impacted by AI technologies. These systems build upon themselves, so it's not just build an app and it's done. They continue to reinforce their learning. The knowledge bases are constantly changing. What was really intriguing about the idea of the oncology treatment system was that system could be constantly updated by the latest New England Journals of Medicine, the latest drug breakthroughs, the latest clinical trials. We have various instances of that system in production now. It's in over 300 hospitals around the world. And the last time I checked, it saw 52,000 patients last year, which isn't a huge number on a global scale, but that's more patients than Memorial Sloan Kettering sees in a year. And that's the #2 cancer center in the world, right? So that's pretty substantial, right? And it was trained by the best doctors at Memorial Sloan Kettering, right? So it's an interesting test of whether we can start to leverage these systems going forward, right? Lots of issues remain behind it. What happens when you train bias into the system, or the information itself is biased that goes into the system, right? The output of the system is then questionable, right? ethics. Doug, I believe you're on the Ethical AI Committee. A lot of companies got together to recognize that there were going to be a lot of questions about the ethics of these systems, particularly as they get into things like law, medicine, radiology, financial services, highly regulated environments. People are going to worry. So the industry is trying to self-regulate right now. That'll work until the government decides to regulate. But we'll start to see, hopefully, progress in that space. I think it's a little bigger than some of the regulatory issues that we faced in other spaces because these systems are going to become pretty powerful over time. Accountability and liability. The great thing about the autonomous driving experimentation that's going on is that elements of those systems are finding their way into the vehicles we're driving today through ADAS system improvements, making every car we drive safer. That's a good thing. The Nissan Pathfinder I rented in San Francisco last year had automatic braking. It did automatic sensory detection of approaching the vehicles too fast from above. It was checking the lanes I was in and making sure I didn't go out of the lanes. And that's a Hertz rental car, right? So we're starting to see these ADAS systems find their way down into the vehicles we use every day, which is just good, period, right? But as we start to get into fully autonomous vehicles, it's going to raise lots of interesting questions about accountability and liability, right? That's going to be a tough one, right? So the conundrum question I always ask around autonomous driving is there's going to be a point in time where a vehicle that's being driven by an AI system faces choices that as humans we would find very difficult. If you go to the right, one person gets killed. If you go straight, a mother and child get killed. And if you go to the left, 4 or 5 people get killed. Which decision does the human make? Right? And stopping is not an option. You can't stop. So the human's going to try to, most humans will try to minimize the loss of life in that situation. And most juries will probably let that human off for that. But if a computer does it, regardless of the fact that it made the right decision, I'm not sure the jury's going to let it off. So where does liability lie? How is that going to work? So that's a very interesting problem that we're going to have to tackle as we start to relinquish control of tasks that humans normally do to machines. Right? We've done that in certain areas. I mean, the computers fly most of our planes, but we still have a pilot sitting there. All right, societal questions, the jobless economy. The good news is this was really talked about a lot a year ago, 2 years ago, that these new systems were going to cause a recovery that was jobless. The good news is the current economy is actually proving not to be jobless. Unemployment rates are pretty high. So we're not there yet, but people are worried that these systems are going to eliminate jobs. I'm in the optimist camp on this. Every time in human history that we've invented new technologies that starts to disrupt and take over tasks from humans, we've freed up time for those humans to go invent new tasks to do. And we're quite good at it, right? So hopefully that we will start to move off. But there is a dislocation time period that occurs as jobs start to fall off from the old systems and the new systems start to come online. And we're going to have to deal with that as a society. And people are worried about what nation states might do with these technologies over time. So lots of issues still to be had. I think we're in a really promising time. I think the technology is at the point now that we're not going to head into a new AI winter. I think we've actually reached the spring, and I think there's a bright summer in front of us. With that, I'm going to turn it back over to Doug.
Okay. Well, thank you so much, Mike. Let's get right to our panel discussion. Let me just move these here, move those ones over. I'll do a little crescent here. Perfect, and let's turn this off. Okay, super, thanks so much, Mike. I would like to invite Mike to come back up here, as well as Frank and Catherine, and let me introduce them in turn. Let's start with Frank. So Frank Tsiribis is the head of Insight Strategy. Did I pronounce that correctly or not? Sure. Your last name? Yeah. Tsiribis? Okay. the head of Insight Strategies and Risk Management, Enterprise Infrastructure Initiatives and Innovation at the Bank of Montreal, BMO Financial Group. He has accountability for leveraging bank business intelligence analytic tools to support ideation and use case development relating to sustaining disruptive and innovative productivity opportunities, as well as implementation a comprehensive risk management framework. That sounds like a great job.
You get to do whatever you want.
Yeah, it sounds like you've got like a piggy bank and a whole bunch of smart people to like mess around with stuff. Kind of like your job at IBM. He was previous. Yeah, well, he was previously the Vice President of Technology Operations, where he was accountability for identifying, measuring, and managing risk across all technology and operation functions. He joined the bank in 2001. He was previously at Capgemini Ernst & Young, and he studied at the University of Toronto, Harvard Business School, the Wharton School of University of Pennsylvania, INSEAD, as a Canadian Chartered Public Accountant and Canadian Chartered Accountant. He's an active member of various global advisory and public policy groups on the area of risk management, emerging technologies, and talent management. We're very pleased to have Frank Tsirbis with us tonight. Come on up. We also have Catherine Hume. Catherine is the Vice President at integrate.ai and a venture partner at FFVC. She's the former Director of Sales and Marketing at Fast Forward Labs. Where she helped Fortune 500 companies accelerate their machine learning and data science capabilities. She is a widely respected speaker and writer on the topic of AI. She holds a PhD in comparative literature at from Stanford University. She speaks 7 languages and has taught courses on enterprise adoption of AI, law, and ethics at Harvard Business School, MIT Media Lab, Stanford, and the University of Calgary of Law. And strangely enough, or coincidentally enough, it turns out that when Mike was the general manager of IBM's collaboration division, and I was running the strategy department in that division, Catherine's father was the head of engineering for that division. So he told us to do stuff, I helped design stuff, and her dad helped build it. So it's a very small world, and we're very pleased to have Catherine join us this evening as well. And come on back up, Mike. So I thought I'd start with you, Frank. From what you saw in Mike's presentation, was there any idea or concept that, when he said it, you're like, yeah, that's what I worry about.
Oh, absolutely. So there was a couple of things actually that resonated. One, I think it was around when you were talking about the knowledge piece and the use of so much information for the computer because of the dimensionality, right? Especially in the medical field, right? And we starting to see that even in financial services. There are so many things that a human brain, like there's a number of dimensions that you have to think about in order to solve a problem. And that resonated with me quite a bit because that's something that we constantly have to deal with in financial services in a lot of domains, whether it be in the cyberspace, in the regulatory space. It is using that knowledge and breaking down the problem in order to do that. I think the other thing that you touched on, which kind of resonated in everything that you said, was the strategic element in applying AI, thinking about the problem. I think you kind of touched on it as you were going through. To figure out the use cases, you need to think about where to apply it in order to avoid, to make it strategic for the organization. And I think the third thing was around knowledge. It's not about the AI application. It is about finding the nugget in the data that you have and turning that knowledge into value for either a shareholder or for an application. So those are, I think, kind of the 3 things. And the last one was around the cost centers that kind of resonated with me because that is it's a cost takeout, but it's also, I think the other thing is it's an experience thing. So we're not seeing the cost takeout in financial services, but you're actually starting to see it as a way of interacting with the customer, right, when you're looking at it, and actually applying some of new behavioral sciences kind of techniques around that area.
Yeah, it's funny, on that one, one of my bank accounts in the U.S. is with Bank of America, and they have Erica. Erica, the new bot, right, that is the banking assistant that helps you go through that. And then how they're introducing that bot through the social networks. Because I see introductions to Erica pop up in my Facebook feeds. Right, so they're finding ways to find channels to get in front of people. So it's going to be interesting how they're driving the adoption of these technologies.
Yeah, it's funny you mention that one because you told us about those robots in Japan.
Yep.
And in Australia, they've got the Get Abby system that is helping, especially elderly people that are coming in and out of hospital and doing outpatient interactions. Mm-hmm. And it's an AI-driven avatar that is getting better engagement and customer satisfaction rates than the visiting nurses were getting.
Kind of like Joe Watson.
Kind of like Joe Watson, I suppose. So that's kind of the world we're living in.
But it's the other thing too, when you were talking about the robots in Japan, we're actually experimenting at BMO using robots in a couple ways. It's one, using them as assistants within the floor actually to eliminate having an executive assistant or letting somebody in. But the more important one is actually we use and we're piloting robots in our HR practices about putting them in areas where you can actually apply for a job. You actually get all the information and so forth that goes along with it. So they're being used in a lot of different ways.
Yeah, one of the on that vein, one of the other experiments that was going on in Japan was could you use one of these robots as a bank teller?
Yeah.
Right. It's one of the same robots. That's another interesting one. And then there was one with a hotel chain in the U.S. is, what's the most valuable person in a 5-star hotel when you go check in any city is? The concierge, right? They know how to get the tickets. They know how to go to dinner. It's all that stuff, right? So the concierge, they exist in those 5-star hotels. So what if you could actually automate what a concierge has knowledge of and make that available in a robotic form as a concierge in the down market hotels around? So there was some experiments going on with that as well. So
or a general manager.
Yeah, well, because general managers don't really do anything, right? So.
Now, Catherine, we talked about, a lot of people kind of think of AI in terms of the end user interfaces that we all interact with, the Siris and Alexas and the chatbots. But as Mike was pointing out, half of the AI problem is the data set. It's the training, the corpus. How, in your experience, how big, well, first of all, how big an issue is it? And second of all, how sensitized are the various different clients that you interact with just how essential an issue it is and how important really good discipline around evaluating it and making sure that it's controlled for bias and all those sorts of things. How big an issue is it?
So something interesting just happened. You were describing the hotel robot, and the answer was supposed to be self-evident, which was, all right, so what's the most important role in the hotel? And Frank said, the housekeeper, and you said the concierge. And that's an excellent illustration of some of the difficulties in building artificial intelligence systems. So one of the things that they depend upon, Mike mentioned during his talk the notion of supervised learning. So this is a technique used in probably 90% of what we call AI applications today in companies, where you have to train the system you have to have the right answer first. So imagine an ordered pair, an X and a Y. You got to tell it what the Y is, so that when you build a function that says, like, all right, here's how X relates to Y, it can learn. It knows it's got that guiding post. It has this North Star, and it can sort of migrate around and say, all right, I've got it. So when and everybody agrees on what Y is supposed to be, so everybody's like, oh, absolutely, it's the concierge. It's like a well-defined problem, right? You can we've got it, we have goalposts that we can move towards. However, when Frank says it's the housekeeper and Mike says it's the concierge, and this happens all the time, this gets really tough. So as it relates to the structure and the quality of the data, one of the sort of key questions companies need to ask when they're starting one of these projects is, all right, how sure are we that two people would agree that the answer is the same? With certain types of structured data problems, so we've got sort of sequences of transactions in time, and we're trying to infer, maybe predict, say, based on somebody's past behavior, what their propensity might be to do something, that thing you want them to do, the business has to sit together and say, all right, we want them to buy. We want them to come into the store. We want them to buy the cheapest one, right? Everybody has to sort of define what that is, and then we can sort of work around and get the data to match the X to match the Y. With some of these more linguistic and human-oriented problems, it gets really tricky because we tend to disagree on things. And so that's one of the sort of rate limiters to adoption. It makes it so that from a process perspective, before you dive in, everybody has to say, all right, are we cool with the fact that this might be the answer? Now, as Mike mentioned, one of the really powerful things that a lot of the consumer internet companies are doing is that they're inverting this paradigm from saying, let's make a system smart by breaking down what smart means to us and sort of programming that into a system, to let's make a system smart by providing a mirror in the form of an app or in the form of some sort of data collection mechanism where it can sort of just take stuff in and become this, like, what's the Lewis Carroll version, right? You go behind the other side of the looking glass version of human existence in the world. Super powerful, and yet it does require thought when we think about, and then when we put an algorithm on to process that, like, how is that going to be refracted, and what are some of the consequences that might incur there? And then we can go down, and I'm happy to talk more about bias, subjective bias, bias in the way that society is existing, where we find trends and patterns in data, et cetera.
How do you, when you're dealing with clients on this, how are they dealing with the fact the system's not always going to be right?
Great question. So this shift from deterministic to probabilistic systems or stochastic systems. So what does this mean, these words that with istic at the end? So if you think about sort of standard computer programming, they automate things and they do the same thing every time. So once we've encoded the program, we're rest assured that it's like, we think it's going to, we do this and then it does Y, and we have a lot of stability over that. When we shift into the brave new world of machine learning, where we're, as Mike said, we're sort of taking an information set and then we're allowing the system, based upon some construct called an algorithm, to sort of discern out patterns. It's going to output a probability that says X is the answer, confidence rate is along some spectrum. So that process, dealing with that, causes a lot of friction in all sorts of industries because they just haven't historically thought that way. In terms of even how they engage with technology, they're used to engaging with technology that doesn't do those kind of things. And they also misread the amount of certainty that they have in making decisions. So let's go back to diagnostics. I'm sure that really great doctors, and we like really great doctors because they're honest with their uncertainty. So when they diagnose a patient, it's not like sort of the baller sales guy who comes in and he's like, it's absolutely the case. You don't trust the person who's like, I'm absolutely confident you don't have cancer, right? You trust the person who provides a little bit of transparency around the fact that he hopes that that's accurate. Based on his best assessment and knowledge, this is sort of what he thinks the case might be. But there's risk associated with that. And we're kind of comfortable with that, but we really struggle with sort of managing these probabilities. And I've seen that cause friction in adoption across just about every industry out there, with gradations as it relates to the context of the business case. So if you're in auditing, say you're Deloitte, and you're auditing 10K statements, you've got to be pretty damn sure that you're saying the right thing, because you're in the business of ensuring that the 10Ks are compliant with a set of accounting principles, and that's your job. When you're Amazon, you're an e-commerce company, and you're trying to recommend the next product for a person, you might get it wrong, but the relative impact to the business is not, Amazon's not going to go out of business, as we've seen. So, but sometimes it does make strange mistakes. I heard about an anecdote today where a woman ordered a coffin for her grandmother, and then she was retargeted around with all of these sort of morbid urns and stuff, which is like, it's this completely ghastly example of where this stuff can go wrong.
Well, Billy,
Yeah, I think the interesting thing on that, I think from adoption viewpoint, is, when we first introduced computers, humans were very wary of them, right? So for decades, we've convinced them that once the programs are tested and they're in place, we should trust the output, and that's kind of the basis for our trust of information technology systems today. And now we're introducing systems that may not always be right. So picking the right use case for how that gets adopted becomes important. That's why I think it was interesting that the industry used games as a way to introduce technologies, because it's less threatening in the way that it's played. In the cases of healthcare, simple use case on the radiology side that I think is helpful but non-threatening at the same time is building a system that does a second opinion of radiology reads. So at night, it just runs a batch run of the radiology reads and comes back and said to the radiologist, not to the patient the next day, and says, you might want to take another look at this one, right? With it in a non-threatening way. But it's a way to introduce a use case that doesn't threaten the user to think that their job's going away or something like that. It's really just introducing it in a way that can be easily consumed and not in a non-threatening way.
So just building on that point, it turns out that we actually let the Watson researchers out of that room once in a while. And when we did,
I know, it's a good story.
it's a good story. But when we did, they walked across the street to the softball diamond, and I actually played softball on the Watson research team. And so we were sitting there after we had lost against GBS or something like that, and we're having beers, and the Jeopardy game had just been on, and I turned to them and I asked them about that question of why it said Toronto instead of Chicago, right? Why did it do that? And they turned to me and they said, well, we don't know. And that, right there, I had this epiphany that I had been used to programmatic systems that had defined logic structures, and if I gave it some input, I could reliably anticipate some output would come out of it, and if it got a piece of output, I could trace that logic chain back to why it got that.
Right.
And this leads us to what has become known as the black box problem. So there are these systems that sometimes they get it wrong, but on top of all of that, there's the question of why it answered this. So one of the big challenges is that in systems that are learning systems that you feed big corpuses, how do we deal with either the black box problem or how close are we to explainable AI? And this then leads into your area. This is the other dimension of risk,
Right, yeah.
and accountability. So how do we deal with this? And is this are there solutions on the horizon, or?
Well, I think there are.
Some thoughts about that?
Yeah,
Go for it.
there's tons, and I'll turn it over to you. But I think it goes back to, it's not a black box. I think there's techniques that we can actually use by looking at the inputs that are being put into the algorithm to see what the outputs are. So you don't actually need to understand all the details of the algorithm. So you can diagnose what are some of the, whether the algorithm is working correctly, but it also understanding not only if it's working correctly, if it's making the right decisions, and is it weighing the right factors when you're going through. So there is a few techniques that you can actually use, but it does touch on the point of use case. What are you using it for? Which it resonated with me. If it's a next best offer on a customer, yeah, it's all right. If you're making a credit adjudication decision, that's a big issue, right, when you're looking at it. So again, the use case and where some of these algorithms are being used is extremely important. I think from thinking about it from a risk perspective, right, and usage perspective, because there are cases where knowingly somebody might have input a variable in there that can introduce, an issue of, diversity issue or, gender-related issues. And we see it especially around, in some cases, just by entering a postal code or a zip code in a particular area in a particular city introduces an issue around
Bias.
Bias, right? So there's a number of techniques that you can actually use.
Yeah,
But-
I really like how Frank framed that. And I think about it when we say, is a system explainable? The good thing is we get to break that statement down. So we can view it at sort of a system level. Actually, there's another good thing too. Systems are not, they don't just sort of appear out of thin air, we make them. So we get to make choices about how we make them. So the one thing is, if you think about the level of a data product in a machine learning system, it's not only this thing that we call AI that is the model in the middle, that basically is a set of mathematical functions that take inputs and they output outputs. It's also all the stuff around that, which Mike was calling sort of the information supply chain, where we can be responsible about what data are we collecting. Are these sensors that we're putting out in the world, are they, how much of the world are they able to take in, and more importantly, maybe what are they missing? We get to decide, what do we want these outcomes to look like? If there's a fairness question around credit risk, do we want to have a certain distribution and make sure that certain people in the population, there's like sort of equal opportunity across people? So we have to think about definitions around what does it mean for us to be fair any sort of question. So there's sort of the outside rim around what data we're collecting, and then also what do we want these systems to do, and can we shape them to sort of try to achieve those outcomes. So there's a lot of intentionality there.
And on the they didn't know the answer. They actually did
I
sort
know,
it out.
I figured it out.
But no, not the what is. The system actually worked the way it was supposed to. The use case changed because it was Final Jeopardy. And because in Final Jeopardy, you have to give an answer. The confidence level on that answer was 3%. Right? So it knew it didn't know the answer. And if it had been the normal part of the game, it wouldn't have buzzed in because it didn't know, it knew it didn't know
And
the
Chicago
answer.
was the second answer, by the way.
Yeah.
It had the right answer the second answer.
Right.
But anyway,
That's a really cool point, though. Sort of all of the hullabaloo around machine learning over the past couple of years has been around the rise of effectiveness in the subfield of deep learning, which isn't all that great often at knowing what it doesn't know. So we sort of have these rules that we put in and we say, all right, if you have to pick a choice, say you're doing a classification, is this a cat or is it a dog? And then we'll say, well, pick the one that has the highest likelihood. And that's sort of this sort of default mode of operations for these systems. And sometimes, the highest likelihood might be like 4%, right? So that might not necessarily be exactly what you want. But there's ways to think about managing that, which is another, it's not quite, can we make the system explainable, but it's, can we work around this question of explainability in a way that can become more
But do you
tractable.
see, sorry, can I just ask a
Yeah.
question? So when you're looking at deep learning, and you mentioned that, right?
Yeah.
Is there that much application out there? Have you seen it in clients? Because
Yeah.
we in financial services, right, we're not using it that much.
It's a great,
right?
yeah.
We're focusing our attention on some of the techniques, whether it be, other AI-related techniques that are not that complex, because again, you're trying to get the adoption, right? You're trying to actually get the user community to accept some of these things and to have that augmented decision-making, right? So, and we see a lot of use cases that can be solved with I would say, less advanced kind of techniques of AI.
One of the sort of fallacies in applied machine learning is that you'll hire a great PhD, and the PhD is excited about using really great new state-of-the-art techniques, and they don't follow the principle of applying the simplest possible algorithm that will scale for your problem, which is kind of the best way to solve a lot of these applied problems. So it's, good old math will often do the job. That said, what's interesting about these deep learning techniques? So when we think about different levels of going from rules to basically allowing a system to learn what is interesting in a data set and then do something with that learning, there's almost like there's like a continuum of the extent to which a human is engaged in the process. Yep. And in as Frank was saying, like most machine learning systems in practice today, they're not using deep learning. They're having a data scientist come in, do some analysis, and then basically like weight different features. So say it's like, will this person buy a product? Well, what's relevant? Income, gender, whatever that may be. Right. And they'll go in and they'll find it and they'll weight each factor and then that'll output something. So when you shift into, like, when would you use deep learning? I think about this with images. So if we think about, say, a system that's going to predict how much a house will cost, what might we use in that model? Where it's located, how big it is, does it have a washer and dryer? We can sort of count the things that might matter and then make sense of it to weigh them. When we get to something like actually text and image and a lot of this wonderfully complex human fuzzy stuff, suddenly it gets really hard. We're fuzzy, and when it's fuzzy, it's really hard for us to figure out what matters, and that's where the deep learning can kind of come in, and it works with data differently. It sort of starts to learn, well, it makes a representation of this data that's then useful for something. So those are sort of fancy words, but it can take something complex and render it in a way that it can be useful for some task. And that's where it's powerful, which means it's like kind of used in Google and Facebook. It's not incidental that these big consumer internet companies are using it most because they have all of this human social data where it's where it would make sense to use some of these new techniques.
okay, let's turn to the audience. And someone out there probably has a question for our panelists. If you don't, I got a whole list of them. There's one right here, Bruna. Oh, okay, Dave.
So we've heard that chatbots and things to deflect call volume are either somewhat successful or not successful at all, and I'm wondering what characteristics have determined that.
Well, I think one of it is if people are building the knowledge base underneath it correctly, because it's all going to, the usability of those systems is all based on whether people are getting satisfactory answers back out of the system, right? And so it's spending the time figuring out the underlying system. If there is not sufficient data, early on we worked on one application where the amount of data available in that domain and the amount of training data available was so small and limited, we came up with horrid results, right? There wasn't enough data to train the system, there wasn't enough data to operate the system. So one of the things that you realize when you're building those systems is there is such a thing as too little data, right? So the size of the data becomes important that you use.
Or too many questions for that data, I guess, right?
Yeah, or actually in some cases there's so little data that it doesn't matter how many questions you have. None of the questions are going to get satisfactory answers because the techniques just aren't going to work on that small subset.
Yeah. The other thing that I would say, especially some of the stuff that we're actually seeing, is the real-time monitoring of the chatbot and the conversation that is happening and the real-time translation of the language, right? So that you can understand when the conversation is going off the rails based on the use of the language, the words are being used, and to switch it over to a human. That is actually becoming one of the areas that's extremely important for us. It's real-time sentiment analysis, right, when you're looking at it. So that's key.
The only thing I'd add is, you know, it's mostly, chatbots these days are actually mostly, there's a little bit of ML, but they're kind of questions where it's kind of the same thing most of the time. It's like an automated dial-up system, but a little bit better than that. The fallacy is, I remember 2 years ago it's a big bank, they had a branch in South Africa, they called, and they wanted to start by making the chatbots say beautiful things. It was like training it on sort of social media data. And it was like, nope, we got to start with like the corpus of like, what are the common questions? I lost my password. Okay, what's the answer, right? However, more interestingly, the company Automat out of Montreal, I think their use of chatbots is really interesting. So they work with makeup companies. So L'Oreal was one of their first adopters. If you think about makeup, you go into Shoppers Drug Mart, and the only expert in the store is the person at the makeup counter, because there's a lot of choices. And I'm not a huge makeup wearer, but which means I'd be a good customer here. I have no idea what to buy, and so I look around and I'm like, I don't know what this is. So what are the ways in which you can go about recommending the right product set to a customer? The one would be the creepy way. So you collect a lot of data on them, and you do comparisons and correlations from person to person and be like, you are the Olay whatever product. The other way is to design a chatbot that can solicit information.
Yeah.
The product, it's a structured information set. It's like, there is a knowledge, it's a constrained domain of knowledge, and you ask the person questions. How old they are, do they have combination skin, do they get itchy? And then via that interaction with the customer, you can sort of scan the space of possible products and find the one that matches. I like that. I think it's a clever use.
But it's a technique that humans use all the time.
Exactly.
Right? It's the same thing a doctor does. A doctor sits down when a patient comes in for the first time. They're going to start asking. They're going to play 20 questions with the patient. It's the first thing they do, trying to figure out, what is bothering that patient, what elements about it. It's the same kind of a process that we as humans do. And so as we build these systems, we have to actually make them interact with humans the way humans want to interact with the systems.
Well, there is a fundamental issue even before you start asking these questions, because our firm had a client, a big telco, and sure, you could, the call center is a big problem. We spend huge amounts of money answering calls, dealing with trying to prevent churn rates, and resetting people's modems and giving them instructions on how to do all this kind of stuff. And sure, you could build an AI engine that could answer all of those things, but what they actually decided to do was to use some simple software robots to every half an hour just run around and ping all the boxes, and any one of them that was having trouble to actually do a reset. And it avoided everyone calling to ask for help. And so even before you figure out how to help people, figuring out how to prevent them asking for help is actually the first question you ask.
Exactly.
Okay, any other questions?
Just to follow up on that.
Yeah.
We work together, so his question is very relevant about the chatbot. But how do you know, because you mentioned insufficient data. If you don't have enough data, putting something there doesn't quite make sense. How do you know when you reach a tipping point?
That's a great question.
Well, your accuracy rate changes, right? I mean, because you're testing it and you're trying to figure out how often you're getting the right answer. And when you don't have enough data, you're shooting in the dark on
Or if you
questions.
have the wrong data. I mean, there's a
Or
bunch
if it's the wrong data. Yeah.
There was a bunch of AI programmers that decided to try to build like a really, really smart chess engine. And so they fed it all of the grandmaster chess games. And so then they sat down to play chess with it, and the bloody thing immediately sacrificed the queen. Everyone's going, what the heck? That doesn't seem like a rational thing to do. But it turns out that at grandmaster level, once in a while, they make a strategic sacrifice of a queen to force a certain position, and it turns out that statistically, the time between that happening and the time winning the game is the shortest of any other move. And so it said, oh, okay, let's go and sacrifice the queen.
Because it's the fastest way to win.
Right. But it was the wrong data set, right? It learned the wrong things, and so it made the wrong decisions.
Right.
Okay, sorry, let's go right back there.
So is trust from the end users one of the barriers to adopting AI technologies? I know that some of the AI technologies, they may be delivering the expected results, but do you think trust from the end users is one of the barriers?
Well, that's where I was trying to make the point about why I think the strategy that some of the consumer companies are doing to capture the interaction model and get people comfortable with asking Siri questions, getting comfortable asking Alexa to do things. What they're doing is they're breaking down the barriers to using information in a different way. So as my expectation for Alexa is as they start putting more and more powerful AI engines behind Alexa, it'll be gradual adoption. People will already be comfortable with asking questions. They're just going to start getting more wide-ranging answers and better answers out of the system because they would have already gotten over the hump of that's how you interact with the next generation systems. So I think the strategy they're employing on capturing the end users is brilliant from a business viewpoint. And two, once you've captured the user interaction model, it's going to be easier for them to evolve the systems behind that without churning their user base. Right?
I totally agree. And I think the more, I know from an FI perspective, right, we're using a lot of those same engines and that social kind of Google and everything else in Alexa. And that's the reason why we're using them as well, right? Because it's a gradual adoption. The trust issue's there. Trust issue then becomes over in the financial services as well.
But I think there's probably a threshold, though, because the reality is we're using AI systems all over the place, right? If you drove here and used Waze or ordered an Uber or looked up the Weather Channel, there's AI all over the place doing all those things, but we don't think much about it because they've been...
Because the functionality of the application is overwhelming the underlying technology principles.
My question was more about the extent of AI application. Like, for example, last year there was an accident with an autonomous which killed a person. So, do you know the trust that was lost? Like, how are we trying to measure that? I don't know. So that's what the question is.
Yeah, autonomous vehicles is interesting because, I think, at least the last time I saw the statistics, most of the accidents that autonomous vehicles have had have actually been caused by other drivers on the road. But there are cases where the autonomous vehicle is going to be in the wrong, and that's kind of the liability accountability thing I was earlier. I actually believe, though, that from a focus point of view, autonomous vehicles over time will be much safer than the experience we have today, especially as everywhere I'm driving, no matter how much you tell people, their phones in their hands, they're doing something with their
They're falling
thumbs.
asleep.
But it's all sorts of interesting distractions in the vehicle for humans. So it's a barrier, but it's just one of those things I think we're gonna have to kind of plow through on autonomous driving. But it's going to be a journey, right? We're not going to wake up and everybody's going to be using autonomous vehicles tomorrow, because I still like driving, right? And so, I'm good. I'm not going to give up my sports car that fast.
Stand over here. Yeah.
I'm just wondering about security. So with fake news and hacking, can AI protect itself somehow to stop using fake data for its calculations eventually? So you could interject, say, fake court cases in ethical law, and then suddenly it's basing it on falsehoods. And I don't know how you'd ever protect it against that.
Well, the whole curation of this, for some of these professional systems, I think we're going to deal with fairly well-curated, locked-down data, right? It's not going to be open for anybody to feed new data in. I certainly don't want open internet theories on medicine plopping into a cancer treatment system, right? And so, I think when you're building these systems in sophisticated use cases like that, there's a whole process around selection, curation of the data going into the systems, and the security around that becomes critical. And it's just like the security around any information system.
Sure.
In general purpose, kind of internet-based systems, I think it's going to be a little bit of the Wild West as these different informations float into the systems.
I think that's kind of one part of the equation. But earlier this afternoon, we were having a discussion about generative adversarial networks, the idea that you've got two AI engines that try to trick each other. One tries to trick the other one, and the other one tries to recognize it's being tricked, and then gives that feedback back to the first one, which tries to trick it again, and they end up training each other and getting really, really good. And it's those technologies that are leading to these things called deep fakes. And you can actually go in front of a camera and do kind of a little dance, and then they can map a ballerina's motions onto you and play it back like you were an absolutely classically trained ballerina. And it's amazingly convincing, and it'll just get better and better and better. And so that leads to a very interesting problem. I mean, this world of fake everything, right? Fake news and what is the veracity of content? Video used to be the last bastion of the truth, and now with AI and these GANs, these generative adversarial networks, even that we have to start questioning, which begs a really interesting question. That in a world where we can generate information that can fool a lot of people, how do we deal with that?
I can't help but address this question historically. I listened to I think it was a Radio Lab podcast, may have been Hidden Brain recently, and it was around sort of fake news. And what's so interesting about it was that in the early 20th century, standards for sort of factual news reporting were really different. So news was written where something would happen, but then to make it so that like a human reader could understand it and appreciate it, they would sort of start with the fact, and then they would sort of embellish it and make it sound like a story. And that was what news was like. And something I don't know enough about sort of the development of like reporting in the 20th century to know at what point it shifted to the standards of what we consider to be factual reporting today. And of course, obviously, with the politics across the various. I'm an American, so I know my way around the American news networks, and it's a little bit less of a technology problem than it is a human problem there too. So that said,
to your point, the fake stuff never went away. I mean, National Enquirer and those things have been around for a very long
no,
time.
but they weren't. The first ones were actually real news. It's just that we would consider it fake, but it was legitimized as real. But but that said, hacking into a system. If you think about a DDoS attack, if you think about the types of problems that information security has been addressing, over the past 20 years. I do think that the impacts are different when when a model in a system can be fooled into thinking that it is accurate, that it is doing the right thing, although it's actually classifying the wrong thing. And like, I actually give a great example of this. My cousin listens to a certain type of music on Spotify, and his dad came in and started to listen to Spotify, and the next thing you know, it was predicting different things. So he went from listening to like Jay-Z to listening to the Allman Brothers Band. And like that sort of shift where, it's not that the system's performance will go down. It's not that there's like just widespread. I mean, there are different types of security risks, but the fact that the system could, from all evaluative purposes, look like it's doing exactly what it's supposed to be doing, right? So from the technologist perspective, they'd be like, yep, working well, and yet the output and the impact for the user is different. That is something to be considered. And I think it's a big security risk, and it's something that is sort of warps our minds when we think about the impact of security. Then there's all sorts of other things that are really the same. So how many queries are being sent to my model? Same thing as how many queries have been sent to my system. So there's a lot of sort of mapping analogs when one thinks about addressing the security issues associated with a machine learning system.
But it's also a very powerful tool, right? So there was a somewhat celebrated case of a hack of one of the casinos in Las Vegas, where some guy had installed a smart thermometer in this big aquarium that they had in the lobby of the hotel. And he thought it was great because he could, from his cell phone, find out what temperature the water was at to figure out if he needed to feed the fish or whatever you did with that knowledge. But it turns out that that device was an unauthorized entry and had established a port into the network, and hackers had gone in through the thermometer to get access to the high rollers database. Now, that's kind of terrifying, but it so happens that this particular casino had used a security system that was powered by AI, and even though the rules in the firewall never said that the fish shouldn't have access to the high roller database, the AI engine was smart enough to say, well, that's weird. What do the fish want with the high roller database? And so the AI engine, even though it wasn't kind of written that way, it wasn't a rules set, it was smart enough and had enough experience to actually shut the whole thing down and call someone in and tell them to go and talk to the fish about doing that. So.
I think we have time for one last question.
Okay. How about two?
Two more. I think
Two more.
Dave's got the...
Oh, okay.
Sorry.
Oh, go ahead, Dave. We'll fit you in.
Very fascinating stuff. You talk a lot about it front end and with Alexa and everything, just from a practicality perspective in an operational world, and I've been part of some large ERP implementations for a long time, but recently was able to deploy an RPA rules-based engine, which also has ML, and starting basics and then layers building up. What I found fascinating, and I'd like to ask your opinion about this and what you guys feel is, always with many ERP systems and any other systems, we've always dealt with bad data. And, big data came about. I remember when IBM was launching a big spiel about big data, and that kind of went off, and Netezza and the whole works. What I'm finding fascinating, and what I'd like your thoughts on, is the data the bots produce are actually clean results that take ambiguity away from users. Silencing some of that was just amazing. From what I found, and if I could say deep learning without machines, humans can now start doing some deep learning on some of that factual data that's coming back. The bots are actually classifying, where they're classifying correctly, and where they're doing their proper alignment to, sending out for us like document packages, doing unstructured data reads, and where their probability is not necessarily 100%, they're pushing that back. But what they are pushing out is good data, and in our case, 100% data in some cases, where now we're fetching that data because it's an open structure, it's not a black box. We can see that data coming back. And we're doing some fascinating decision making on that data. What are your thoughts on that? Because could be bot reading good bot data and starting to do analytical structures on that.
I don't know if I have thoughts on that.
I think it kind of, no, I think what you're getting at is kind of what, it's similar but not the same as what Doug was talking about the reinforcement of systems on each other. So the output of one AI system becomes the input for another AI system, right? And so what you're starting to say is that you're using particular AI techniques that's generating cleaner, better data, that you're now starting to build a new level of initially probably analytics-based information on it, but you'll probably go beyond traditional analytics on that data as it goes forward. And you're going to start to see that these things sort of compound as the systems go along.
Okay, let's see if we can just grab one more here. Yep.
There you go.
Well, thank you very much for letting me ask our last questions. And I think a lot of you guys mentioned a lot about user experience. So I remember someone telling me the big difference between machine and human is human has an empathy. I just want to ask you, do you think, is there anything as a practitioner we can do, maybe embed empathy into the AI machine learning solutions?
Well, there's, so I'll tell you one piece that this goes back to the discussion I started on the robots in the home environment. One of the things that Son, the chairman of SoftBank, is trying to do with Pepper is he's actually, all his programmers and hardware guys are working on how to build emotional response, empathy kind of things into the robot to try and to detect emotion on the part of the person they're interacting with. So there is work going on in that space. I don't know how far they've gotten yet, but that's what they were doing in the research labs when I was there.
I think it shows us empathy is a magical thing. Like, think about how complex it is. I'm here in my head, and I can project what I think you might be experiencing. Okay, that's weird. And then I can feel something similar to you. That's so complex, right? So it helps it helps us basically think about reorienting what kind of problems qualify as intelligent. So we mentioned throughout tonight a lot of these hallmarks in the history of AI. They also are great user interface design hacks where we represent a mathematical problem as a game. Arthur Samuel, who built the checkers playing system in 1952, has wonderful things to say about why he thought he should sort of show all this abstract math that's so hard for us to visualize as a checkers playing game. And we think about that as a sort of a really intellectual activity, just like chess and just like Go. But it's a really complex and amazing activity for us to be able to do what is empathy, to feel something similar to what somebody else is feeling. And so for me, it's kind of it's a wonderful, the fact that that's so hard is it forces us to ask really cool questions about us, you know what I mean, and what we experience. And so there are some systems that are sort of mimicking, paying attention to somebody's emotional response and then providing almost what looks like it would be empathy, which might be enough, and that's also an interesting question.
Yeah, so but there are those, right? There's the let's consume a whole bunch of people demonstrating empathy and then use that as a model to kind of imitate that behavior.
Yeah.
But on top of that,
But the key word is the one you just used, which is
is
imitate.
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 I understand,
That's
but that leads us to the second class, which are, we already talked about, these adversarial networks that are actually being designed to understand what the other side of the equation is thinking and how it looks at the world in order to try to find a way to trick it. And so we're starting to even develop the technology to have that, incorporating the other point of view into your thinking to develop a strategy. So we're well on the way to doing that.
So I can empathize with all of you
Because they're
who want to
hungry.
ask more questions. So I would invite everyone to continue on the discussion. We've got the room where we originally met. Come on back for some drinks, some food. Continue on the discussion. Our panelists will be there. You can ask them questions yourself. And let's have a round of applause for our panelists. And on behalf of all of us at the Burning Group, I'd like to thank you all for coming tonight. We hope to see all of you for drinks and food, and we look forward to continuing the discussion. Thanks a lot.